So this is the lecture on contrapositive proof. It's the second method of proof we're going to talk about. We talked about direct proof before. So remember, the contrapositive of the statement P implies Q is not P implies, not Q implies not P. So let's look at some examples as to how we're going to do this. Oh, and first, remember, these two logical statements are equivalent. We've shown this in class. But let's look at an example here. And so here's the proposition. We want to show that if xy is odd, then what? Then x is odd and y is odd. This may sound familiar to you, and it should, because we proved this in the last video when we did direct proof by cases, and it was rather long, and now I'm going to give you a proof that's actually very short by using the contrapositive. So first, let me just identify P for you. So this is our P statement. So if x, y is odd, that's our P statement, and then our Q statement is x is odd and y is odd. So if we want to write the contrapositive of this, we'd write not Q implies not P, and then let's write out what this is in English. So not Q would mean that x is even, and then the and would become an or, y is even. So if x is even, or y is even, then not P would be the statement xy is even. So xy is not odd, or we'll say xy is even. And so if we prove this statement, then for free we get P implies Q. Because remember, P implies Q is equivalent to, it's the same as saying, or logically they're equivalent to saying not Q implies not P. And you can look at the truth tables, which we've done before, but if you look at the truth tables of these two logical statements, you'll see that they are the same. All right, so let's prove this. So proof. So let's let x and y be integers. And we want to assume, one of these is going to be even, because it says x is even or y is even. And remember that statement without the loss of generality? We can use that here because we can assume x is even, right? But that would be just like assuming that y is even and seeing what happens. So what we can say here is we can say WLOG without loss of generality, right? Without loss of generality, what? We may assume x is even, right? So we can assume x is even, or we could assume y is even. It really doesn't matter which one we pick. We get the same result in the end. All right, so when we assume that x is even, and then what? So then what do we know? We know x is equal to 2 times a, where a is an integer. So a is an element of z. And this is by definition of even. And then notice what? Notice we can rewrite this x times y to be equal to what? Well, x is 2a, and then times y, which is really equal to, you can say 2 times b, where b is equal to a times y, which is also an element of the integers. Hence, xy is equal to 2b So xy is equal to b is even, by definition of even. And we always like to end with that sort of therefore. So therefore, xy is even. And so that ends the proof. Remember that without loss of generality, what that really means is that we could do this proof again, but instead of doing it with x is even, we can assume y is even, but the same result will occur for the same exact reason. So instead of doing it twice, we can say, hey, there's no difference really between x and y in this proof, so we'll just say without loss of generality, this is the case. Also notice how shorter this proof is than the last proof we did by cases. So the last one had like 4 cases, and this one is probably a fourth of the length. So sometimes a proof by contrapositive can shorten the length of the proofs in general. So let's take a look at another example here. So here's one more example we're going to do by using this method of proof called contrapositive proof. So here we have let x and y be integers, and if 5 does not divide xy, then we want to show that 5 does not divide x and 5 does not divide y. So let's identify our p and our q. So this is our p right here, and then this is our q right there. So we have p and we have q. And we want to write down the contrapositive. So remember, the contrapositive is not q, implies not p. And so here, if this is q, not q would mean that 5 does divide x. So if 5 does divide x, and then the and would be translated when you do not to an or 5 divides y, then not p would be 5 divides xy. So 5 divides xy. So this is what we want to prove. So let's write proof. And so we'll let x and y be integers. So let x and y be an element of z, period. And then we have either 5 divides x or 5 divides y. So let's do this one in cases, although you could use without loss of generality here because this statement here is symmetric in x and y. But let's do it in cases. So case 1 would be, right, suppose 5 divides x, then what? Right, so then we can say, then x is equal to 5a, where a is an integer. And this follows by definition of divides. By definition of divides. And then notice what? So notice here that x times y then, x times y is equal to 5a times y, which is the same thing as saying 5 times b, where b is equal to a times y, and it's an element of the integers. All right, hence what? Hence xy equals 5b implies what? Implies 5 divides xy by definition of divides. By definition of divides. And so we won't write therefore yet because we have one more case to do. So let's do case 2. So case 2 would be suppose 5 divides y. So case 2, suppose 5 divides y. And you'll notice that our argument here will be exactly the same. That's why if you wanted to, you could say without loss of generality, we can assume that 5 divides x, and then proceed from there, do this, and say therefore 5 will divide x times y. But we'll do cases here just to get some extra practice. So suppose 5 divides y, and then we write exactly the same thing. So then y is equal to, so you can still use the same letter if you want. You say equals 5 times a different a. So these a's are not the same. Even though they're the same letter, they're actually not the same. It's sort of like this proof is kind of done for this part. And so we could start a new proof and assume that a is different. So then we'll define it, where a is what, where a is an integer. But remember, these a's are not the same, so don't get confused by that. By definition of divides. You could also make it a different letter. You can call it c if you want. Definition of divides. And then again, we say notice what? Notice if you take x times y, that's equal to x times 5a, which is the same thing really as 5 times x times a, which you could rewrite, and this is because multiplication is commutative, and which is equal to 5 times b, where what? Where b is equal to xa this time, and that's certainly an integer because integers are closed under multiplication. And remember, this b and this b are not the same b, but we can reuse a letter if we redefine it again, because again, this proof right here is sort of done, and then we're moving on to the next step, the next case. So hence, xy is equal to 5b, which implies what? Which implies 5 divides xy. Therefore, by case 1 and case 2, what do we get? Therefore, 5 divides xy. If you want to write an additional statement like by case 1 and case 2, you could. But it's not necessary, really, by case 1 and case 2. And so that completes this proof by contrapositive. And remember, so now we prove the contrapositive, we can get this one for free. P implies Q. So if 5 does not divide xy, then we know 5 can't divide x, and 5 can't divide y. And so that completes this video. And so just as a recap, right now we have 2 methods of proof. We know how to do a direct proof, which is the most basic type of proof, which is a P implies Q. And then we also know how to do a contrapositive proof now, which is basically proving P implies Q, but instead of proving it directly, we'll prove the contrapositive, not Q, implies not P. And we get P implies Q for free if we prove this. One of the reasons we may want to do a contrapositive proof, because it may turn out to be easier to prove the contrapositive than it is to do the direct proof. An example of this was given right here. This proof we did in the last video when we did direct proofs with cases, and it was quite long. There were 4 different cases that we actually that we considered, and you can see that this proof is just a couple lines. So sometimes a contrapositive proof is a lot shorter than a direct proof. So that's sometimes why we want to use it.